The great thing about coming to CppCon is you get to see many, many interesting people and many interesting problems that are solved.
All right, the title of this talk is This is C++, and my expectation is that everyone in this audience already knows what C++ is. I'm going to cover C++ from the point of view of what is C++ for. What is C++ trying to accomplish, and how does it accomplish it? Understanding this is important for two reasons. The first is that we have a better understanding of how best to use C++, and I think that's why most of us are here. We want to use C++ better. The second reason is that it helps us to consider how C++ should evolve. Understanding what C++ is trying to accomplish guides us in designing new language and library features. In this talk, I'll explain what C++ is trying to accomplish and how it accomplishes it. I'll give some examples that illustrate this. I'll then consider something that I consider one of the most important points of controversy facing C++ today, and we'll see how an understanding of the defining aspects of C++ illuminate that controversy. Finally, we'll discuss the implications of this insight for one of the biggest challenges the C++ community faces. So the first question is, what is C++'s superpower? And I want to answer the question, what is C++'s superpower? But before I tell you that, what I think the answer is, I want to explain that C++ has several superpowers, and none of them is unique to C++. Some people might suggest that C++'s superpowers might be flexibility, portability, expressiveness, etc. These are important, but at its root, C++'s superpower is uncompromising performance. We try to design C++ to maximize flexibility, portability, expressiveness, safety, all these things, but never at the cost of performance. Why do we make this choice? Because this is C++. That's the right answer. Just shout it out. There you go. All right. So when we're faced with a trade-off between better safety at the cost of performance, we don't accept that trade-off. Why not? Because this is C++. All right. Members of the Standards Committee understand this. Understand this and what's expected of C++. And that the definition of C++ can, quote, leave no room for a lower level language. What this means in practice is that although we may add various features that provide us with high level abstractions, allowing us to reason about code at a high level, we don't add features that violate our zero overhead rule. Now, sometimes this is misunderstood to mean that features must have no overhead, which seems to come from the name. But the zero overhead rule states that features, when not used, must incur no overhead, and if used, must incur no overhead greater than what would be required to implement the feature by hand. So, how does C++ provide uncompromising performance? I think there are several ways, but I think the key one is that the user's code is implemented directly with corresponding machine language instructions if they exist. For example, if the user's code calls for adding two integers, then we implement this with a machine language instruction to add two integers. Division is implemented with an integer division instruction if one exists. But you say, surely every language does this. Well, not necessarily. Let's look at these examples. So they illustrate what I'm talking about. These operations are implemented with single instructions. But let's look at the functions. Are they safe? How about add? How could that fail? Integer overflow. And the same thing is true for multiply. Now, we don't need to worry about integer overflow for divide, but what's the problem there? Potential problem. Dividing by zero, right. All right, so all of these functions represent some safety concern. So our challenge is that what we'd like to be able to do is have C++ compilers generate code for ideally all platforms that is efficient and can be generated efficiently on all platforms. Unless there's a bug in the hardware, all the platforms are going to yield the same result for the non-corner cases. But different platforms will handle corner cases in different ways. So if all platforms behave the same way in corner cases, we would just define that's the consistent behavior of what our language is. Of course, we could pick one behavior and then emulate that on platforms that don't support that behavior. But the issue there is that part of the cost of emulating a particular behavior for corner cases is doing so is going to slow down the non-corner cases. That is, the common cases would be inevitably slowed down by trying to emulate some type of behavior. So in C++, we don't define behavior in corner cases. You could imagine a language that prioritized safety, defining some reasonable behavior for these cases. For example, there might be a few options for what we might do in division by zero. We might, for example, make the result be the maximum integer value. It's as close to infinity as we can get, right? Okay. We might throw an exception. We might set some static error flag. There's a number of things we might do. The actual behavior turns out to not be important for this point because any kind of implementation is going to require us to have to make a test in all cases to determine if this is the corner case. So let's take a look at what I've created here, this div safe. So what it does is it returns the maximum value. It's about the easiest possible way you could implement something that handles division by zero. But notice what the cost is. It produces twice the number of instructions, and there's a test in there. These are performance killing. This is significantly more expensive because we added this safety. Right? So keep in mind, what we're doing here is the simplest possible thing in the case of division by zero. We're not throwing an exception, we're not setting some error flag, we're just returning a constant. But the cost is that there's twice as many instructions with a branch. So rather than take this safe C++ approach, C++ opts for performance. Why do we take that option? Because this is C++. All right. All right. Now, someone might point out that we don't always take this route. Consider std vector, the index operator. This provides element access without range checking. But in addition, the standard library provides the @member function, which provides the same service with range checking. This is a rare case where C++ offers both a safe and an unsafe operation. Excuse me, an unsafe option. So the important thing to note here is that in practice, which one is used? Almost always it's the index operator. So if there were only one option offered, which option would that be? It would be the index operator. It would be the unsafe option. Why is that the option we would offer? Because this is C++. Now, you might argue that this is a false feeling of better performance because it is a logic error to attempt to access an out-of-range index. Therefore, somebody's going to have to do the checking. If we don't do the checking in the library, all we've done is shift the burden to the caller. So we're not any better off. But that's not really the way it works, because it is possible that the caller's code is going to do a number of different accesses on the same element. We might do a couple of reads and then a write. And in that case, we only have to do the range check once for a number of operations. If we call the add operation, it's going to do that range check every time. But it's even worse than that, because most of the time we access a vector, we do it in a loop. And we've set the loop up in such a way that we're not going to have an out-of-range access ever. There's never a reason to do a range check. So if we have the range check built into the operator, it's a waste of time every time in those situations. So this leads us to this observation that's often made, that you can build safe on top of fast, but you can't build fast on top of safe. Now, what does that mean? What we're saying here is that if we have an API that does no checking, then we can put code on top of it, calls that API, that does the necessary checking, any checking that absolutely needs to be done. And then what you've got is a fast API with a safe call on top of it. But if you have an API that does checking at every access, if it's ever unnecessary, it's impossible to build code on top of it that turns off that checking, right? So in most cases with C++, in the C++ library, that's the option that's done, is there's very little domain checking performed in C++ library calls for this very reason. That makes things, that puts a burden then on the caller that it's up to them to make certain that the call is safe. Why is the library designed this way? Because this is C++. All right, so I believe that the superpower of C++ is undefined behavior. It's the fact that we put constraints on what can be called so that what is called is guaranteed to be executable with uncompromising performance. So are there any corner cases in our ability to implement code with uncompromising performance? Then we put the burden on the programmer to express their idea in a way that avoids those corner cases. That gives us the ability to generate code of uncompromising performance. And why do we do this? Because this is C++. All right, so the particular example I'm going to show you right now will actually be treated a little bit differently in C++ 26. The details will be different, but the larger point is still there. So for our purposes today, let's assume that the code I'm talking about is up to 23 and not up to, it doesn't include 26. If you're interested in the change for 26, you can read Thomas's paper there. All right, so here's the example. Now, C++ allows us to declare variables of fundamental type without initializing them. Note that the expectation of some naive users is that this code results in A having the value of 0. Experienced C++ programmers know that that's not the case, and sometimes the reason we get to be experienced C++ programmers is because we made that wrong assumption initially, and that's how you get to be experienced, right? All right, so why is this? Well, it's because if the value, the variable that we're declaring is immediately going to be set with some runtime value that is coming from the keyboard or reading from a file or the network, then setting it when initialized would in fact be a waste of resources to do that. So given the choice between a behavior that leads to fewer bugs, and in fact this may have lots and lots of bugs still in the wild because of uninitialized variables like this, could be, but we have a choice between eliminating those variables or compromising our performance. We opt for uncompromising performance. And why do we do this? Because this is C++. All right. So it's not the point of this talk, but I think the syntax could have been safer without compromising performance. One can imagine a language in which declaring an uninitialized variable does mean 0, and if you want it to not be initialized, you would say somehow like this. So we could say that int a by itself does mean to initialize to 0, and if you really don't want the compiler to spend any time initializing it, you could do something like this. In fact, this is actually legal today, and that's exactly what it means. If you say this, you're just basically saying don't initialize this. And it's very clear now what your intent is. You don't accidentally think that this is going to be 0 initialized. So you could also imagine, because this is undefined behavior, that we could just define the behavior. At some point in the future, we could just say, oh, yeah, it's now 0 initialized. Is that going to break any existing code? If the code depends on undefined behavior. I think depending on undefined behavior is itself undefined behavior. So I think we're safe here. It wouldn't break anything. But, so this would be a fix of lots of in-the-field bugs right now. And yet we don't do that. Why do we not do that? This is C++. Because this is C++. All right. Let's drill down on the potential safety issues of an uninitialized object like the one in this example. What is it that we can legally do with an uninitialized variable? What is not undefined behavior? What can we do with this that's not undefined behavior? We can assign to it, obviously. And there's one other thing that we can do to it, and that is, okay, I would say taking the address is not done to it, but about it. But let's not quibble on that. The other thing is you can ignore it. You can let it go out of scope. You can destroy it effectively, okay? All right, now, is it legal to read from it? It has to have some value. We don't know what the value is because it's uninitialized, but it has to have some value, right? So can we read from it? Well, yeah, it's going to have some value, but the standard explicitly says this is undefined behavior. Reading from it's undefined behavior. All right, so sometimes I have students in class when I talk about things like this, they'll say, well, can't the compiler warn us about these kinds of things? And the answer is, yeah, in some cases it can. And if you have static analyzers, there might be more situations it can warn you about. But the issue is that that's not really the compiler's job. The compiler's job is to keep track of the types of variables, not their runtime state. And so in some simple cases, the compiler can maybe analyze that, but it can't do it in the general case, particularly if you passed something to another function. So let's take a look at this. So if this function were compiled in another translation unit, the compiler that's doing the call doesn't know what the body of the function is, and the compiler, when it's generating the body of the function, doesn't know what the compiler is passing in. So without some kind of whole program analysis, there's no way to detect that there's undefined behavior. Does that make sense? All right. So the question I would have, when you're writing the preconditions for a function like this, would you indicate that the parameter being passed has to be initialized? Some people say, yeah. Most of us are silent because we realize, no, we probably wouldn't have mentioned that. If you were looking for documentation of this function, would you expect that to be called out? No. Why? Well, it's obvious. We're expecting that be initialized. Technically, we could pass in something that wasn't initialized, but we would just expect that that's initialized. If we pass in uninitialized objects into functions that take things by non-const reference, we're in a lot of trouble. All right. So in my day-to-day use, I almost never create and rarely think about uninitialized objects, but they are in fact part of the language. In Elements of Programming, Alex Stepanoff and Paul McJones defined a term for the situation where the compiler knows the static type of an object, but its runtime value is not fully formed. They coined the term a partially formed object. Now, the very existence of partially formed objects is a risk to inexperienced, naive, or careless programmers. Why do we accept this trade-off? Because this is C++. All right, so the analogy I'd like you to think about is, this is the way I think about it, it's a ski run. Imagine you have this really well-groomed ski slope, and if you stay on the defined path, you can safely ski at full speed. But if you wander too close to the edge, you have rocks, trees, crevasses, maybe even a cliff, right? So in C++, if you stay within the bounds of what's defined behavior, the compiler can generate safe code of uncompromisingly fast performance. But this can only be accomplished because we only support, that is, define the behavior for the most common cases for most operations. And we place the burden of avoiding the cornered cases on the programmer. Now, that might be quite a bit of burden in some cases, but why do we accept that burden? Because this is C++, right? Okay. So, why is the undefined behavior of C++? Why is, sorry. All right. Why is C++'s undefined behavior, why is it superpower undefined behavior? Sorry, couldn't get that out. It's because that's what allows us to guarantee that the code that we do accept, the code that is defined, can be generated to have uncompromisingly fast performance. All right, so I've been making the point that in C++ we live with a number of safety trade-offs that puts burdens on programmers. This might lead you to think that C++ is unsafe. And in fact, many people have made that claim. But this claim fails to understand how applications are developed. It rests on the belief, trivially true, that that compilers produce the code that we run. But the deeper truth is that applications are produced not by C++ compilers alone, but by the C++ ecosystem. Compilers and the language definition are an important part of creating applications. But so are tooling, testing, documentation, the availability of high-quality libraries, training resources, language cultures, and most important of all, programmers. The C++ ecosystem has always been hyper-aware of memory safety issues, and this is an important part of our language culture. And it is reflected in the work of the Standards Committee, as each release of the standard finds new ways for us to provide memory safety without compromising performance. C++26 is providing support for new and powerful tools focused not only on memory safety, but other issues of code reliability and performance. All of these that we will get without compromising our uncompromised performance. So believing that safety is the sole responsibility of the compiler is to misunderstand the application building process and is likely to result in misguided attempts to build in safety at the cost of performance. Further, a logic error in a memory-safe language is just as fatal as a logic error in an unsafe language. The belief that the use of memory-safe languages precludes the creation of buggy applications is a false sense of security that could get people killed. Imagine an all too likely scenario of a manager that mandates a trendy new memory-safe language that is so new that it doesn't have a ready pool of experienced developers, well-developed culture, or training resources, who then skimps on tooling to detect bugs with static analysis, or training so that the developer team doesn't know how to understand valuable techniques like programming by contract. The likely result will be an expensive, buggy software with poor performance. Experience has shown that C++ applications developed by well-trained engineers with access to state-of-the-art tools and techniques will have better performance and be as safe or safer than applications developed in languages with less robust ecosystems. The industry investment in C++ means that not only will these applications have a performance advantage, but likely also have a developer cost advantage. So mandating that safety be built into a language definition is no guarantee of a safer final application, but it is a guarantee of mistaken performance trade-offs. So C++ has been and remains a valuable development tool due to its robust ecosystem and its high performance standards. So with the C++11 standard, which is sometimes called modern C++, we introduced move semantics and a syntax for R-value references. This is a major complication of the definition of C++. As someone who makes their living, which I do, teaching modern C++, I can assure you that understanding move semantics and R-value semantics, R-value references, is a major challenge for both novice and experienced C++ programmers. Including move semantics in C++ represents a major cognitive load for the payoff of fewer unnecessary copies, and also perfect forwarding. And it may be the single most difficult to grasp feature of modern C++. Why did we add this language complication? Because this is C++, and we do what we must do to achieve uncompromised performance. Unnecessary copies compromise our performance. So let's look at a specific example of move semantics. In this constructor, we can move initialize a data member, avoiding what might be an expensive copy. So what do we know about the list move constructor? Is it a constant time operation? Is it inexpensive? Is it non-throwing? So move operations should be cheap, constant time, and non-throwing. So here's the vector move constructor, and it is guaranteed to be no except. It is also cheap and constant time. But for the move constructor, the standard only guarantees constant time Why is this? It's because, in my opinion, the committee has made a mistake and compromised our uncompromised performance. So let's step back and do a quick review of move semantics. I first want to exclude a set of problems that might arise in legacy code bases or code that has irregular types. So let's stipulate for this discussion that we won't be working with any legacy types which don't have move operations defined, or any types that have data members that aren't movable because they're const or references or arrays. So if you have modify access to the source for all our types, then we can create all our types such that each data member is one of three categories. It's either a primitive type, an owning pointer, or a compound type made up of primitive types, owning pointers, and compound types. So given this, we can make all our types have cheap, constant time, non-throwing move operations with just following these rules. Shallow copy the primitive types, copy and then zero out the source for any owning pointers, and using the move operations for compound types provided by recursively following this rule. Does everyone understand what we've just done? Right? Pretty straightforward. Is this all we need to do? Almost. It's one of the things we need to do. We need to make certain that our destructor can be safely called on a move from object. Now, normally that's not an issue, but we do have to make sure the destructor doesn't make any assumptions that wouldn't be valid for move from objects. Okay, now is that all we need to do? There's more space on the slide. Yeah. So there's one other thing we need to do, and that's assignment. Assignment also needs to be safe when we're assigning a move from objects. Now, why is it important that we support this? Well, it turns out this is a very valuable use case. We have algorithms that rely on moving a value from one element so that it can be replaced by a value from a different element. So this is the heart of sorting, inserting, removing, and uniquing on random access containers. So these two use cases, destruction and assignment, were identified in the very first proposal for move semantics, which, take notes quick, it's N1377 by Hinnett, Dimov, and Abrahams. It described leaving move from objects in a state that is, quote, a self-consistent state. And then parenthetically, it added, all internal invariants are still intact. But in practice, many users took this to mean valid for destruction and assigning too, because these are the only use cases that were called out. Even though the actual wording says all invariants are preserved. Most or many people did not follow that. So let's note in passing that these are the exact two operations that are supported for uninitialized primitive types. You can assign to uninitialized primitive types and you can destroy them. And those are the only things you can do them. So in other words, the interpretation that these people were using follows what Stefanov and Paul McJones identified as partially formed objects. Their static types are understood by the compiler, but their runtime values are not fully formed. Now, let's return to vector and list and what I said was the committee's mistake. So the standard says that objects of type defined in the standard library when moved from are in an unspecified but valid state. Further, they define valid as supporting any operation that has no precondition. In other words, these are what Alex and Paul would call fully formed objects. So let's look at the implication of this difference for vector. The standard doesn't specify how vector is implemented, but it's an allocated array, and we can determine that there are three required data members: a pointer to the allocation, something that tracks the size of the allocation, and something that tracks the number of current elements. Note that this size and capacity can be implemented with either an integer or a pointer. What I'm saying here is true for either implementation strategy. So imagine we have allocated an array of integers and the data members are in the state, right? So we're pointing to some buffer. The buffer has a capacity to hold 16 integers, but currently we only hold 10. Okay? All right, now, what is it going to look like after we move from it? Well, if we use the rules that we've just introduced earlier, then the allocation goes to nil, And the primitive types are copied and unchanged. This is the minimum amount of work you could do to move from a vector. This is the moved from result. Okay? But the standards committee has specified that a move from object, if you call and ask it its size, then it always has to work because size has no precondition. Is the size here going to be correct? No. So, well, okay, let's come back to that, Greg. So if we do the traditional implementation of size, the trivial implementation, we just return the size, then we have a problem because this move from object doesn't actually hold 10, integers doesn't hold any. So one way of changing that is to change the size member function so that it first checks to see if we're moved from. But notice now we've added a performance burden for every time you call size, because first it has to check to see if we're moved from. So I assume Greg's kind of kidding when he proposes that that's an option, right? This is going to be an issue. All right, so what this means is that a standard implementation of vector move has to zero out the size and capacity because you could call size and capacity under the standards guarantee that anything without a precondition you could call. So that means that the move is no longer of uncompromised performance. You have to do extra work. Okay? Now, of course, you could point out that's not much extra work. Zeroing out 3 words is something the compiler can do really fast. But notice, this is the vector case. Let's look at the list case. Now, it turns out, and remember, the list doesn't require that move be no except in the list constructor. The standard doesn't say it's that. So the reason is that some implementations of list, the standard list, use a sentinel. And according to Wikipedia, a sentinel node is specifically designated node used with linked lists and trees as a traversal path terminator. This type of node does not hold or reference any data managed by the data structure. In other words, it's just a way of letting us know that we're at the end of the list. Okay? Okay? Now, I'm not going to take a position on whether this is a good idea or not. It's an engineering decision. It has pluses and it has minuses. So one of the trade-offs is now that when we allocate a node, we're also going to have to allocate this sentinel node. And then when we destroy the node, we'll also have to destroy the sentinel node. But that's just once on construction, once on destruction. No problem. There's nothing to be worried about there. Until we think about what if we're going to do a move construct. We're constructing a new node, so it doesn't have a sentinel yet. Do we want to take the sentinel from what we're moving from? Well, that's obvious, yes. Take the sentinel from what we're moving from. But then what are we left with the moved from object? Now, if the only thing we require of a move from object is that it be destroyed or have something assigned to it, then we don't need a sentinel. But if you say, no, 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 everything that the move from object would have to be able to do in the non-move from state still has to be able to do, then it has to have a sentinel. So the move requires allocating a new sentinel. And that might, in fact, throw. So you see now why the standard says that the list move constructor doesn't have to be no throw. Okay, so you might ask yourself, why would a library implementer choose to use sentinels given the implications for move operations? Well, as I said, there's trade-offs. There are advantages to using sentinels. This decision was made before moves were even proposed, and it was because there's some advantages to the library to using sentinels, and moves were not on the radar yet, and in order to not break the binary, not break pre-existing code, the library implementers are kind of locked into this. And the standards committee recognized really it should be no throw, but we're not going to force this on a library that otherwise is working. Okay? All right. So the additional cost to vector, from what the standards committee has said, is pretty minor, but the additional cost to list and some other, not just list, but basically any of the node-based types, is potentially pretty significant. But my main objection to what the standards committee has said is that by documenting what you do, what you can do with an object that's moved from is that it's encouraging people to make logic errors. If you're moving from an object, it makes sense to give it a new value. It makes sense to destroy it. But it doesn't make any sense at all to ask it what its state is. If you need to know its state at some point, don't move from it first. Right? That's why I say this is a logic error. And I think the Standards Committee, by documenting what you can do with a move from object, is effectively encouraging people to think, well, that's a good thing. The committee said I can do this. Well, you can for committee operations, but to do so, I believe, is a logic error. So when I explain to my classes that a move from object should only be either destroyed or assigned to, you can see the tension in the room start to go up when they realize there's a burden placed on them. As soon as they move from something, it's on them, not the compiler, but on them, to see to it that nothing is done to it except be assigned to or destroyed. But when I explain to them, that's not hard to do, because you will only move from an object when you know you either want to assign a new value to it or you want to destroy it. It's not hard to track this. It is a burden on us, but it's not a hard burden, because if you weren't going to assign a new value to it, or you weren't going to destroy it, you wouldn't have moved from it in the first place. So I was pointing out this to a friend of mine that's a standard library implementer. Now you may be thinking, the way I talk about the Standards Committee, that I probably don't have any friends there. Some of you are actually thinking, the way I drone on about C++, I probably don't have any friends at all. But I do. I didn't ask him for permission to use his name, so we're just going to call him Inigo Montoya. So I told Inigo, there's no other use case for moved from objects other than destroying them or assigning to them. But he said, no use case we've discovered yet. Okay, that's true. But to be fair, it's now almost a decade and a half since we've had move semantics, and we've created hundreds of algorithms, and it seems unlikely that we'll discover a new use case now. But then Inigo gave me an example. He said, suppose I have code that populates a vector with a series of pushbacks, and then moves from the vector, and then it loops, and then it does pushbacks, and then it moves. Now, if I don't have to destroy the vector, I don't have to assign a new value to it, I can assume it's empty because I moved from it. Well, he's a standard library implementer, he knows what the code does, but the standard doesn't guarantee that if you move for something, it's empty. Furthermore, being able to do that is using this extra work that we're requiring to do, and it would in fact be less extra work to simply assign to it in the case where you have moved from it and don't plan to destroy it, or not leaving it perpetually in a situation that it can be assumed to be empty. It's costing us performance to be doing that. So I have a couple of answers then, but more importantly, this is still calling for this compromised performance, because the savings in the rare case where we do make the assumption that it's default initialized is more expensive than just default initializing when we really need it. So why did the committee make this rule? If it has these performance implications, why did the committee say that? Well, I think from the committee implementer's point of view, I understand. We have a term for invariants that don't always hold. What do we call invariants that don't always hold? Not invariants, right? Library implementers get uncomfortable when you start talking to them about having their objects in a state where the invariants don't hold. That's not supposed to happen. But of course, the thing is, invariants don't always hold. Suppose I have an object in the stack and I call its destructor. Can I call members on that object? No, of course not. Its lifetime is over. I think that's the way we should think about move from objects. Now, the lifetime is not completely over because you can assign something to it, but the lifetime of the object is frozen. it's been suspended, right? A move from object is effectively a suspended object. Its lifetime is waiting to be destroyed or waiting to be revived by being assigned to, and nothing else should be done to it, and you should not make any assumptions about its state or the behavior of its invariance in this point. All right. So there may in fact be more of a motivation, and I think part of the hint comes from this, from a blog post of Herb Sutter. His blog from February of 2020, which was simply called Move Simply, explains that move from objects of what he calls well-behaved types will not be treated with any special restrictions. So this blog post is intended, in part, to remove the burden that I place on programmers to track move from objects and restrict what can be done from them. Herb is saying, don't worry, move from it. It's just like any other object. You don't have to do anything special. You don't have to track it. You don't have to think to yourself, oh, I can only assign to it or destroy it. He's trying to remove this mental cognizance. Now, I want to point out, I'm going to disagree with this, but I don't want it to seem like it's personal. Herb is literally my boss. I'm the chair of CppCon. Herb is the president of the foundation that owns CppCon. He's my boss. So this isn't personal. I have a great deal of respect for what Herb does for the community. I'm all on board, but we have a difference of opinion in this technical world, so we're going to explore that. So the blog post uses this phrase, well-behaved types, because the committee can't make a decision to tell us how to write our code. But in effect, it can. And the reason I say that is because if the standards committee says you pass something in the library, the something you passed in the library has to meet some requirements, well, that's pretty much all of our code. Who would write an object that you can't put in a vector or some STL type, or you can't use with threading or something like that, right? It's just, that's the way it is. All right, so if you read Herb's blog, I want you to read all the comments. In particular, I want you to read the comments from Sean Parent. Sean points out that in the standard, this appears, there's actually a couple of appearances of this is somewhat close. And so it has a note. Now, notes are non-normative. It means they're not considered actual part of the law of the standard. They're used to explain things. So it's not actually part of the standard. It's just explanatory. But in this case, the implication is pretty clear. What is being said in this note is that if there's a requirement on an object being passed into the library, that requirement is still there even if the object's moved from. So in other words, it's saying if there's an invariant, that must still hold even if the object's moved from. So Sean proposes this as a thought experiment. So what do we have here? We have an array of 2 items. The items themselves are unique pointers, just a unique pointer to int. So what do you see what we have? We just have an array, array of pointers, and each pointer points to an int. Now we want to sort these. So we call sort, we give it the beginning and the end of the range to sort. Everybody see what we're doing here? And then we pass in the comparator. Now in this situation, what are we going to do? Well, we're going to compare the unique pointers, but we don't want to compare the address that the pointer points to. That's not what we want to compare. We want to compare the value, right? Everybody see what we're doing? We're comparing the pointers by what they point to. So the comparator does a dereference. Anybody see a problem with this code? A properly implemented sort function is going to do this properly. There's no way it would not. Very straightforward. But notice, this violates the note in the standard. Does everybody see why? Because if the item is moved from, if the unique pointer is moved from, can we dereference it? No. Will this sort ever dereference it after moving from it? Will it ever do a compare after moving from it? No. It does the compare and then does a swap if the swap is necessary. But it will never call a comparator on a move from object. So this is guaranteed the sort function, if written properly, works, but according to the note in the standard, this is undefined behavior. So in order to fix this, the real way you'd have to write the comparator is to say, well, if the unique pointer is not currently empty, then do the compare. But notice, we're adding performance to do a check that is never going to be necessary. It's only necessary if we follow what the note says and have to make this work. You see the issue? So that was Sean's example. All right, so Sean claims that what the note should say is something like, this is when moved from the object is assignable to and destructible and not otherwise specified. Okay? All right. So if you want to know more about this, Sean has a talk called Find is Broken, and you can see that from on our YouTube channel on CPP from 21. All right, so I believe that the blog's approach creates this illusion of safety. In other words, it's saying, don't worry, you move from an object and then you can call it, but the problem is the call itself might be safe, but you might not be in a state that it makes any sense to do it. You've created a logic error in your code, and all you've done is you've said, oh, the call can be made, we're gonna crash later on because we've made this kind of logic error. We haven't thought through what we're trying to do here. So one of the pleasures of researching this presentation, it gave me a reason to reach out to two of my C++ idols, Howard Hinnett, who was one of the original authors of the first move semantics proposal, and also Sean Parent, who was Alex Stepanov's boss and the champion of generic programming and value semantics, and who pointed out this issue with Herb's blog post. So Sean sees this particular issue, and that's why he wrote this talk. You can see where Sean's thinking is that. From Howard's approach is a little bit different. What Howard is saying is we should go and look at every single algorithm in the standard and call out the specific requirements of that algorithm. Now, I don't disagree with that. I think that's a very good idea. And we're never going to have an algorithm that requires anything from a move from object other than it be given a new value or destroyed. There's just no use case for it, and there's no situation in the library where it's ever going to be done. And I think that's great. But the difference I have with Howard is that I also believe we should be teaching people not to do anything with a move from object except that. Howard is saying, for example, the standard should allow you to sort a vector with move from objects as long as your comparator understands move from objects and can use that. And I just say that's a logic error. So I understand what Howard's saying. The library should be as useful as possible, and if it's possible, do what you want. But I'm saying if you have a container with moved from objects in it, you should not be trying to evaluate how they should be sorted. All right, so we'll move on. So let's consider the semantics. Sorry, this is the proposal that Sean is working on and Howard has promised to help him with. So let's look at these two signatures. What is the meaning of these signatures? Now, I think the first means that there's a couple of different ways to look at this. The first is that the called function, the first one, may modify its argument, but must leave it in a state that does not violate invariance. The second can mean one of two things. It either means that the function may modify its argument, leaving it in a partially formed state, or it means the exact same thing as the first. If we follow what Herb's blog post is saying, these two things mean the same thing. You have to leave the widget in a valid state with all the requirements still met. If you accept my point of view, then what you're saying is that the second one doesn't mean that. The second one means you can leave it in this partially formed state. Do we really mean for these two signatures to mean the same thing? All right, so I want to look at one last example. So suppose you're working on some operating system and it has this expensive to create really cool object of a magic 3D rendering that's driven by an AI model, and it's something wonderful and terrific and great, but it's expensive to create. So we call this create viewport, and it returns some viewport ID, and when you're finished with it, you call free viewport, and it returns this. Now, what is a viewpoint ID? Well, it's either a pointer to some data structure within the operating system's memory, or it's an index into something in the operating system's memory, right? And there's a bunch of things you can do with viewport IDs, like get the dimensions, or in this case, the X dimension, right? Everybody understand what we're doing here? All right, now, I look at this and I immediately think, wow, this is a perfect candidate for wrapping in C++. Everybody get the same idea? Anybody get the same idea? Yeah, absolutely. Let's do that. So we create this thing called viewport. The constructor calls create viewport. It has a single data member here that's the viewport ID. And then in our destructor, we call free viewport. And then we have a whole bunch of accessors to get the dimensions and things like that from this object. Does everybody see what we're doing here? All right, perfect mapping, great. Now, how do we implement the move operation? Well, I think what we should do is the move operation simply transfers the viewport ID from the object being moved from to the object being moved to, and then we zero out the viewport ID. Now, if the only thing we ever do with this is destroy it, remember what the destructor did? What did the destructor do? I guess am I going backward? I'm going backward, okay. What did the destructor do? We just said, if there is a viewport ID, we free it. So that's going to be safe for destruction. I didn't say how we would do assignment 2, but you can imagine a pretty straightforward assignment 2 that's going to, if it's a move assignment, it's just going to shift the VP ID over, and if it's not an assignment, it's going to have, that will be an expensive object. We will have to create a new viewport at that point. So that's how I think it should be done. But that does not meet the requirements of the standards committee. Why? Because what happens when we call some, get the X dimension on this? How do we do that? We don't have a viewport ID to pass into the operating system function. You see the problem? Everybody see the problem? All right, so what do we do about that? Well, there's a couple of different ways we can do this. One is we could call the OS and make a new viewport whenever we do a move. Anybody like that idea? What's wrong with that? It's very expensive. The whole point of moves was to avoid doing this kind of expensive stuff. So that's not great. There is another thing we could do. How about this? We could modify all the member functions to fake something when moved from, right? It doesn't really have an object, but you can call it and say, well, what are your dimensions? And maybe it always returns 0. Well, what's the color? The background color? Well, the background color is black. We could lie in a bunch of things. Notice what this means. You're going to write a whole bunch of code that first has to check, is this object in the moved from state? If it's not, I'm going to call the OS and do the right straightforward thing that would be really easy and trivial to write. But now we've got this. First we have a check. And then if it's not moved from, we call the OS. If it is moved from, we make up some silly result. Now, notice that silly result's not doing anyone any good, so it's useless. Also, you have to write a lot more code because you have to check for it and all this. And that code will actually be executed in the normal case. So you see the performance implication? Anybody like this solution? I don't like this solution either. I don't like either of these solutions, right? So I think that, to me, the obvious thing is to treat a move from object as something that you will only either destroy or assign to. Those are the only things. So to summarize, what is C++? It's uncompromising behavior. That is the purpose of C++. And how do we achieve this? We achieve this by living with uncompromised, with undefined behavior, which gives us this safety trade-off that says if the programmer stays within the bounds of what's defined, the compiler is going to generate uncompromisingly fast performance. The Standards Committee disagrees, and I should say the Standards Committee has only put this in a note, and Herb put this in his blog, so there's still time to fix this intent of the Standards Committee. The Standards Committee has said, though, that standard types, when moved from, are still effectively fully formed types. Now, that ship has sailed. I think it's a mistake. I think the reason it's a mistake is there's some minor performance hits in some cases, there's major performance hits in other cases, but the most important thing is it's leading to logic errors. You're telling programmers, move from this thing and then do something creative with it. That's a logic error, right? But that ship has sailed. And even I wouldn't want to change it because there are possibly code out there that relies on that guarantee. I don't want to pull that out. And most of the things in the standards committee don't have huge performance impact. Most of the things are not like the example I gave you of the viewport. That is, in our world, more than in the standards committee itself. Okay, so the committee's direction, based on the note and based on Herb's blog post, is that for user code, move from is fully formed. And I think the advantage to that is you have this minor reduction in cognitive load. You don't have to care about something when you move from it. But as I point out in my class, that's not that big a burden because you only move from it if you plan to destroy it or assign a new value to it. It's not a heavy burden to do that. The committee's saying, okay, well, we can remove that burden. I don't think that makes much sense. And for some use cases, we will have either unacceptable performance or we have this tangle of code that we write that is just slowing down our non-move from case and giving us extra code that we get to test and maintain. All right, I believe that the correct way to think of move from objects is if something's moved from, it is now a partially formed object, meaning there's only two valid things to do with it. You either assign a new value or you let it go out of scope. All right, there's one other thing that I want to make a point of, and that's the safety thing that I said. And again, it's because C++ language is getting safer and safer. We're adding new ways that, if you look at the standard, we're adding new ways to write code safely, but always without compromising performance. We can have both. We can have safe software with uncompromised performance. And how do we have that? Why can we do that? Because this is C++. Thank you very much. We have 3 minutes or almost 3 minutes for questions. Anybody have questions?
Hi, thank you for the talk. So in the unique pointer example, you mentioned that we can call only functions without preconditions, but dereferencing has a precondition, so it's not actually...
Maybe it's an echo. I'm not hearing you very clearly. Can you slow down just a little bit?
In the unique pointer example, dereferencing has precondition that it is not null.
Right.
So it's not... Because before that you mentioned that moved from object, you can call anything that doesn't have a precondition. So you can't call dereferencing, for example.
Yes, but notice that in the situation that the way Sean had written the code, there was never a case where he was going to do anything from something dereferenced, or from something that was nil. In other words, he knew that sort was going to do a swap, and at some point, the unique pointers might become empty because they were in the middle of a swap. But he also knew there should never be a dereference of that during that state if sort was written properly. So in other words, the code as written should work. The problem was that the note implies that it should work in cases that would never happen. That comparator should work even if you try to do the comparator with a move from object. But in Sean's case, there's never a time when a move from object should be compared. He doesn't pass in a move from object, and the algorithm itself should never move from an object and then say, oh, should these be swapped?
So the note says you can call, you can dereference moved from unique pointer?
What the note says is, the note is saying the comparator is wrong, because the comparator should be, you should be able to call that comparator even on move from objects. And even though the standard, the sort will never do that. But the standard is saying, you as someone passing this in, you have to pass in a comparator that could be used with move from objects.
Thank you.
John, I appreciate your talk and brilliantly argued. For the record, I agree with you. But there is one case that is particularly problematic, and that is self-move assignment.
Yes.
Particularly in templated or generic code.
Yeah. I believe that I believe that Howard has changed his position on this. His initial take was that it should be the burden on the caller to figure out if self-move could happen, and they have to check for it themselves because moves should be just as fast as possible. But I believe Howard has recognized that there are cases where it's difficult to determine that self-move can be happening, and so it's better to build the safety into the move. But I'm not really taking a position either way because it's not that doesn't really impact my argument. But you're absolutely right. It's a sticky area.
Thank you for the talk. To play devil's advocate for a moment, if automakers had objected to the inclusion of seatbelts in cars because they added weight and so impacted performance, I think people might have stopped trusting them to make decisions that impact society. When security professionals and even governments are recommending that people stop using C++, is it perhaps time as a community to reevaluate our priorities?
Well, I think our priority is to make C++ as safe as possible without abandoning the point of C++, which is uncompromised performance. If we say, okay, well, we're going to make a bunch of changes to the compiler so you can't do stupid things, but every option is now some percent slower, I just think I just don't think that's what we're trying to do. Now, there are languages that are saying we're going to take a completely safe approach and we're going to be as fast as we can be, and good luck to them, right? But I don't think it makes sense for C++ to abandon what C++ is about. I mean, I'm not trying to make light of the situation at all, but I think we've demonstrated that we can ship. There are fighter planes up there that run on C++. It can be done. We can write safe C++. Maybe you can't do it with engineers that don't have the right tools or the right education. Maybe but we can write safe C++. And I don't think that abandoning what C++ is about, which is uncompromised performance, is a win. We're out of time. I'm going to take Dave's call. Thanks for the question.
Yeah, hi, John. So for your consideration and everybody else's, we have a type, it's movable, it contains a socket or communications thing, whatever, right? So we move from it, whatever. We happen to know that when you move from it, it goes back to its default state, whatever. So we write a unit test. We make a thing and we move from it. We want to make sure that the new thing that we move to has got all the right stuff, so we do that. In the unit test, we want to check that the moved from thing no longer owns it. So in the unit test, we do operations on the move from object to make sure that it has been moved from. Our static analysis tools complain about the unit test. Right? Do we shut up the static analysis tools and say, no, it's okay, we know what we're doing? Or do we re-engineer something about our unit test so we don't have to look at the move from object to see if it really got moved from properly? I haven't decided yet. This is a code review I have to deal with on Monday.
And I'm not
just to consider.
I'm not prepared to give a decent answer without thinking about it more clearly. I see the problem, and I have a solution, but it's so half baked I don't want to share it. You have a quick one?
Quick one. Do we have? Thanks, John. By the way, do we have, or might we one day have a move sanitizer?
I don't know if there is a move sanitizer. It does.
We have thread sanitizers.
No, I appreciate it. I don't think there is.
Move would be a great thing.
I think that we would have to have some kind of settlement of this particular issue, because as I said, it looks like the standards committee is going one direction, and I would say I'm not really certain that the whole committee is. This note got in there somehow. Herb has opinion. I'm not certain that the rest of the standards committee is on board with that direction. But I'm raising the flag that says we should be cognizant that that looks like the direction they're going.
Okay, thanks.
Hopefully quick. This is more picking out your experience over time here. When I first learned about move semantics, the way you explained it was my understanding, right? Like once move from only write into or let it go away. There's no other usage of it. And the article you linked to was from like 2020. So has this been like a thing that's evolved over time where people kind of changed the opinion from the origin, or is it just my data sources where I learned were, saying one thing versus this?
I think it's been a progression where the first thing was we're really focused on performance, and then the standards committee discussed what should a move from object look like for standard objects. And again, the library implementers, which is what the standards committee is largely dependent on, is what do the library implementers say? The library implementers say, I don't really want it to be in a way where my invariance, and for most standard objects, a move from object can be really easily reset to just an empty object because they're not the kind of example I gave you. And so the node-based problem that uses sentinels, that was an exception. It was like, oh, but they still said, well, we'll just say a move from object. It's basically an empty object, and it's pretty cheap in most of the types in the standard. That's a pretty cheap thing to implement. There's a little bit of overhead, but it's reasonable, and it was considered reasonable overhead most time. It's constant time for the most part, and it's going to make it safer for users. And they just looked at it that way. They didn't look at it like, when I had the conversation with Howard, one of the things I said, remember, we have a bit of a disagreement about what the correct direction is. I said, the problem is you need to teach people how to think about move from objects. And what Howard said is, we don't have enough people on the standard who think about training and teaching.
I would agree. That's
right?
the big problem.
They think about library implementation, and so they were saying this is a simple, safe thing that we can do. It's only constant time. It's not that much overhead, except when sentinels are involved, and so we can do this. So that's why I think it evolved. And then, having gotten to that point, I think Herb's saying, well, if it works for the standard library, why shouldn't it work for everybody? And if it does work for everybody, then we don't have to worry about this cognitive burden of having to keep track. And I just think, whoa. Somebody needs to stand up and say, no, there's something going on here that you're not seeing. So we've gone over a little bit. We need to all get over and get ready to see the plenary. But thank you all very much for coming. Thank you very much.